Okay, so let me finish this slides as soon as possible. Okay, so let's skip this part because of so many equations. I don't like it either. Okay, but here it will be more important about constructing efficient frontier. I know maybe some of you are familiar with that, but anyway, I still have to review this part because this is a very important section in building the portfolio, especially about the most original portfolio theory based on the Markowitz efficient portfolio, efficient frontier theory. So this is about how to plot the efficient frontier, because in previous codings we just generate one efficient portfolio for a given return. So in this case, we just specify the return to be equal to 0.005. Okay, so this is a required portfolio return. So based on this return, we like to find the optimal weightings for three assets. But what about we change the specified return? Okay, in this case, if we change to 0.006 or 0.0087, etc., and we can generate as many points as we can. So we call these as efficient portfolios. So based on these efficient portfolios, we can plot the efficient portfolios in the x-y axis. So in this case, you will see here on the x-axis will be the standard deviation. So this is about the variance, okay, the square root of the portfolio variance, and the y-axis denotes the return. So how can we can generate this plot? Because every point on this plot here denotes the most efficient portfolio, which means for a given rate of return, we can find the minimum variance portfolio. Okay, so so in this case, in this coding, you can see we are just following the same codings in the upper part, as we mentioned, as we have discussed in finding the GMVP. Okay, but here we just create a sequence of returns. So you can see this is our base. Our base is to generate a sequence. Okay, we have a minimum return, maximum return, and the length equal to 100. So that means we try to generate the 100 point of given returns, and based on this, we can apply this return, this sequence of returns to this function. Okay, and finally we can generate the square root of the portfolio. Okay, so this S denotes the square root of variance based on a sequence of returns of the portfolio. So S denotes the sequence of the standard deviation of portfolios, and R base is the return we specify. So this denotes the portfolio returns, and S. So usually we have a plot, we're followed by the X and the Y, right? X denotes X is S. S is standard deviation of portfolios, and the Y is the portfolio return. So we can plot this result. So you can see this is the final result we get. So usually we call this plot as a efficient frontier. Okay, but sometimes we can generate many different portfolios within this area. Okay, but on the outer bound, of these plots, this denotes the most efficient portfolio. So what we are trying to find, the portfolio is the most efficient one. Okay. So this is one way to generate the efficient frontier, but there are another way to generate the efficient frontier. So this is a fast way to compute the efficient frontier based on theory. We can just use two efficient portfolios to generate the other efficient portfolios, which means we can just use a linear relationship, okay, by combining two efficient portfolios together, okay, so that we can generate efficient portfolio here. Okay, so in this case, we can have X and Y. Okay, X will be a frontier portfolio, and Y will be another a frontier portfolio. So by combining these two together, we can generate the different efficient portfolios on the frontier. So this is the basic logic behind that. Okay, so based on this, then we can just set up an alpha. So this alpha is an arbitrary number. Okay, so what we are trying to do is to linearize the portfolio X and the Y, and we can generate a portfolio Z. Okay, so Z will also be the portfolio lying on the efficient frontier. So we can change alpha to many different numbers so that we can generate as many Z's as possible. So this is how we are doing here. So this is the covariance. And besides that, we can also calculate the covariance between X and the Y. Okay. And also we can also calculate the Z portfolio variance of Z. Okay, so you can see this is very similar equation as we learned before. We can just use Z plus sigma Z, and we can find the results. Okay, so the first problem is to find the Z, and based on Z, we can find the sigma p squared Z and the sigma xy. Okay, so based on this, we can generate our efficient frontier. Okay, in the following, we can just use two portfolios lying on the efficient frontier. Okay, in this case, the first point we're gonna select is the GMVP, because we mentioned that a lot. GMVP is the easiest one that we can find. So GMVP is the first point and the first portfolio. The second portfolio is an arbitrary portfolio. You can set up to be any portfolio for given rate of return. Okay, so we have two portfolios here, and then based on this, we can generate the results. So now you can see the notation change a little bit. We now use M, okay? So we use alpha multiplied by M plus 1 minus alpha multiplied by X. So we can find the solutions, we can derive the result here, and finally we can plot the efficient frontier. Okay, so this is how we are doing in this case. So in the following codings, we just use the same strategy. Okay. So now you can see here, we generate a sequence of which A denotes the alpha in our equation. Okay, A is alpha. So alpha starts from 1 to -1, and interval is negative 0.1. So we can generate the many points, okay? And then we can set up the number of points we wanna we can define the number of points, okay, so that we can use length of A, and then we can also generate the Z matrix, okay, and we can so you can see the Z matrix is matrix 0 NA dot 3, okay, so we have so many rows, we have 3 columns, okay. So in this we have NA rows, we have 3 columns, so we can save our result in this matrix. Okay, so now what we can do here is to just run the equation in the following. So I think the one that we can be sure about is the sigma dot mx. So this is about the MVAC. Okay, we can go back to the equation here. So what we are doing here is, you can see this is M plan sigma and times x. So M plan okay, so M plan is the weighting for the GMVP. Okay, M plan is the weighting for the GMVP, so you can calculate this easily. Okay, so this is weighting for the GMVP, and the X is the weighting for the portfolio X. Okay, because portfolio X is the efficient portfolio for given rate of return. So we can easily calculate that without any problem. Okay. The only thing we have to make sure is that X portfolio is also an efficient frontier. Okay, you can find any efficient frontier you like. You can set up any given rate of return. You can find the weighting for this X. So this is the first 2 things you have to provide. Okay, so the weightings, you can see here the weightings for M and the weightings for X. So you have to provide these 2 data first. Okay. Okay, based on this, then you can run the looping in the following. So for example, we start from the 1 until n dot A, and then you can generate a sequence of mu z and the sigma 2 dot z. So that denotes the expected return of the portfolio and the variance of portfolio z. So based on this, you can plot the result. So finally, in this codings, we just plot the results, and then of course you can just do some modification to the plotting. This is not that difficult, but you can see this is the final result. Okay, so we have a global mean. So this is GMVP, and this is the Microsoft. In this case, we set our value, we set our portfolio return to be equal to Microsoft. So we find this GMVP, so this is GMVP, this is M, and this is the MVP with a given return equal to Microsoft. So this is X. So based on this based on the GMVP and X, we can generate so many points along the efficient frontier. Okay, so this is a very simple case to construct the efficient frontier. Okay, so the title is to construct efficient frontier with 2 efficient portfolio. So now in this case we use GMVP and MVP with given return equal to MSFT. Okay, so you can construct this efficient frontier based on these two portfolios. Okay, and then we can move a little bit further, discuss another problem. This is about the capital allocation line. What we are more interested is that, okay, now suppose we have risky assets. We also have cash in our hand. So what will be the efficient frontier like? What would the efficient frontier be like if we include risky assets in our portfolio? Okay, so in this case, the efficient frontier will become a straight line. So in this case, we are talking about how to allocate our capital. So now we are talking about a line called the capital allocation line. So in other words, the capital allocation line is the efficient frontier line for our assets. But now this line becomes a linear. So in this case, usually we would like to find the tangency portfolio. Okay, so the tangency portfolio T is the portfolio risky asset that maximizes sharp slope. So if we have a risky rate of return, we call this as RF. So we have a portfolio return minus the risk-least rate of return divided by the standard deviation portfolio. So this is about the Sharpe ratio. So now we have another optimization function. In this case, we have a Sharpe ratio, which is to be maximized, and also we have a constraint. Okay, so this is subject to constraint. So this is the you can treat this as a weighting. Okay, so don't get yourself be confused with the notation here. So T here also denotes the weighting. So this is this is the same as we saw before. We use W or X to denote the weighting, but now we use T. So T plan times 1 equals to 1. So that's the sum of the weights equal to 1. Okay, so in this case, we just plug in the T and we will see this is our Sharpe ratio. So now it becomes very straightforward. We just need to find the maximum, maximize. We just need to maximize the Sharpe ratio. Okay, so this is a very simple question right now. So what we can do right now is to generate. Also, we can generate a Lagrangian function for this problem. Okay, so this is the Sharpe ratio here. This is Sharpe ratio, and this is the constraint. Okay, and we can also take the first order derivatives with respect to T and the lambda, and finally we can derive the result. So this should be used T star. Okay, T star equals to this formula, but you can see very clearly it's quite similar to the GMVP formula. Remember? Let's go back to the GMVP here. Okay, so this is a formula for GMVP. We have a sigma inverse times 1 inverse times sigma inverse times 1. But now you can see this is a tangency portfolio. Okay, tangency portfolio, but now you can see the 1 is replaced by mu minus RF times 1. Okay, so this is very similar. The only difference is the 1 term here. Okay, we replace 1 with the mu minus RF times 1. So it's very similar. Okay, anyway, based on this formula, we can find the tangency portfolio. Okay. Of course, there are some other notice here. You have to pay attention to this. So if the risk-free rate is less than the expected return of the GMVP, and the tangency portfolio usually has a positive Sharpe ratio. But if the risk-free rate is equal to the GMVP, is equal to the expected return of the GMVP, then the tangency portfolio is not defined. So sometimes we can't find the tangency portfolio. Okay. And last one is if the risk-free rate is greater than the expected return on GMVP, and in this case, we'll see a negative Sharpe ratio. Okay. Okay, so this is about the mutual fund separation theorem. We just mentioned that if we only have two assets in our hand, one is risky asset, the other one is riskless asset. Okay, in this case, the efficient frontier will become a straight line instead of a hyperbolic line. Okay, so this is totally different. So you can see the new efficient frontier, okay, is a line connecting the point RF to the unique point F. Okay, that point will be on the old efficient frontier. That will generate a line tangent to the old efficient frontier. Let me see if I can. Okay, so you can see the plotting here. Originally, we have an efficient frontier, but right now, if we have riskless assets, okay, so in this case, we will generate a new straight line, and this straight line will also generate the tangency point. So what we are looking for is the tangency portfolio, and that denotes the most efficient market portfolio. Okay, so this is our final goal. We need to generate this plot, but before we generate this plot, you have to know how to find the tangency portfolio. Okay, so in previous slides, what we are doing is to find the tangency point. So here is the simple example here. Okay. Okay, so let me finish this. After we find the tangency portfolio, then we can construct the tangency line here. Okay, so if we go back to the chart here, okay, based on this, if we can find the tangency point, and we also know the riskless rate, then we can construct the linear line. Okay, so this is because this is a linear equation. So what we can do is to write the equation. So what will be the equation like? So now you can see based on this derivation, then we can write the equation to be this way. So this is the portfolio return. Okay, so you can see here, this is the portfolio return will be equal to the riskless rate of return plus XT. So XT is the share of wealth in tangency portfolio. Okay, because you can see if XT equals to 0, all our assets will be allocated to the cash or the riskless assets. In this case, it's a treasury bill. Okay, so the larger the weight of X is, the more allocation will go to the risky assets. So this is a straight line here. So xt times mu p t, okay, mu pt is the tangency portfolio minus rf. Okay, so how to find the mu pt? First of all, we need to find the tangency portfolio weightings, okay, which is t plan, which is t. So we can calculate this value. So the first step here, okay, just like I mentioned here, the first step, you need to find the solution of t. How to derive the t? How to get the t? You just plug in the formula. Okay, so this is the easiest way. Okay, plug in the formula, get the t, and based on the t, you can derive the tangency. You can derive the tangency portfolio line, okay, which is straight line, and then you can also calculate the sigma pt and the sigma pe. Okay, so sigma pt is the standard deviation of tangency portfolio, because we already know the weightings. Okay. Okay, and the sigma PE is the portfolio the portfolio standard deviation of the portfolio we construct along the straight line here. Okay, so this is how we deal with the problems based on the capital allocation line. Okay, so in the following is a very simple example, and I use this example to illustrate the problems we have just mentioned. So now we have a three-firm portfolio example: Microsoft, Nordstrom, and Starbucks. But basically, these data are based on the data in Excel or CSV you can download from the trunk class. Okay, because I already uploaded the trunk class, so you can see here. Okay, so this is the data you download, and you can also calculate the mean value for each stocks, and also you can calculate the covariance for 3 stocks, and finally you will get the values like this one. Okay, so you can also verify if the numbers here are correct or not. But basically, it's pretty close. Okay, it's pretty close. You can just verify the results. But now we have some practice. Okay, so this is a three-firm portfolio. So now you can, for example, the first problem is that assume the risk-free rate is 0.005. Okay, try to find the tangency portfolio, expected return and standard deviation, and the Sharpe ratio. Okay, so how to do that? Based on the equation we just learned. Okay, so now we have a risk-free rate. Okay, so the question is to find the tangency portfolio. So let's go back to check out the tangency portfolio here. So how to find the tangency portfolio here? Okay, the tangency portfolio denotes T, right? The tangency this is the weighting for the 3 assets. So we just plug in numbers into the equation, right? Plug in the numbers into the equation, then we'll get the tangency portfolio weighting. So the first question is sigma inverse times mu minus RF dot 1. Okay, so how to do that? So mu, what does mu mean here? Okay, mu should be this mu I, right? Mu I is denotes the average or historical average return of Microsoft based on our data. Okay, so we have mu I Microsoft, for Nordstrom, for Starbucks. Okay, so we just plug in the numbers. So let's see our coding. First of all, let's just check our codings here. Okay, before we check our codings, let's just review the formula. So on the upper part, we have sigma inverse multiplied by mu minus RF dot 1. Okay, so based on this, we can use the so first of all, let's say RF equals to 0.005. Okay, and then we can also generate the inverse of sigma. Okay, so this is the coding to generate the inverse of sigma. And then we can also generate the one vector, and also we can generate the mu minus RF. Okay, that denotes the mu dot vector minus RF dot multiplied by one vector. So this part denotes this one, mu minus RF dot multiplied by one vector. Okay, so this denotes this part. Okay, so based on this, then we can find the top matrix, on the top here. Okay, on the top we have sigma inverse and multiplied by mu minus IF. Okay, so this denotes this one. Okay, so this is the numerator part. Okay, inverse of matrix multiplied by this, and in the denominator one, that will be easier. So now you can see in the bottom one here, we just use the transpose of one vector multiplied by the top matrix. Okay, so you can use this and combine them together, and then you can find the t vector. Okay, so the t vector denotes the weightings for 3 stocks on the tangency portfolio. So you can see Microsoft will have 1.02, and Nordstrom will have a negative 0.32, and Starbucks will be 0.299. Okay, so this is the same as the slides here. Okay, so this is how we calculate the weighting for the tangency portfolio. So is it okay now? Are you confident that you can do this question by yourself? Is it okay? Not really sure. Okay, because I have codings here. Okay, so you can refer to my codings, but don't worry, because now you are using R. Basically, I mentioned that before. Right now, the R is providing the Copilot for you. Okay, the Copilot, of course, Copilot is the AI tool to help you to generate the codings. Okay, so if you want to save some time, because from my viewpoint, I would suggest you to load up the Copilot to help you to write the codings. I will show you some examples later. Okay, because I have to use my notebook to show you how to use the Copilot, but I can't use the server edition to show you Copilot because it's not working here. But anyway, this is just to help you to save some time. Okay. So this is the tangency portfolio, and then based on the tangency portfolio, you can you can find the expected return and the standard deviation. So expected return, okay, expected return. Okay, expected return is to just plug into the equation here. Just plug into the equation T transpose of T multiplied by mu, and the standard deviation will be this formula. You can just plug in this formula and you'll get the result. So here is the coding. Okay, if you want to get the expected return, you can just use mu T. Okay, and I use gross product to finally to get the result, and then I can use I can also use the formula to find the result. So expected return will be 0.051, and the standard deviation will be 0.1115. And finally, you can also calculate the Sharpe ratio. Sharpe ratio will be 0.4202. So you can verify here, okay, on this table here, you will get the result. Okay. Okay, so you can try to replicate the result because I have a few numbers here. Okay, at the bottom here we have weightings for 3 assets. On the right hand side here we have portfolio expected return, standard deviation, and Sharpe ratio. But the most important is the weighting. You have to find the weighting first, then you can derive the numbers on the right hand side. Okay, so let's take a break and we'll be back later.